Hello, everyone. I hope you are all doing well and safe. On behalf of SPE Egypt Young Professionals, I would like to welcome you to the final and last session for today's course. My name is Ahmed Haytham. I am the fresh graduate petroleum engineer from South University and the e-mentoring head at SPE Egypt YP. And I will be your moderator for today. Before we start, I would like to remind you to please drop your question in the Q&A section below, and please keep the chat box professional and ethical. Now, without further delay, please give a warm welcome to Engineer Ahmed Samir, who will be giving the third and final lecture of our short course that consists of 3 webinars on hydraulic fracturing. Engineer Ahmed Samir is a qualified frac engineer with more than 12 years of experience in oil and gas industry, with extensive experience in all kinds of frac techniques in addition to experience in completion design for oil and gas wells. This includes over 100 frac jobs performed using all frac technologies such as highway, foam frac, foam highway, clear frac, roadship proppant, and fracturing of extensively deep high temperature formations. He is an author and co-author of many technical papers published at national and international conferences. Also, he is a qualified stimulation training instructor. Engineer Ahmed Samir is holding both bachelor and master degrees in petroleum engineering from Cairo University. His current position is the Petroleum Engineering Department Manager at Agiba Petroleum Company. Now I request Engineer Ahmed Samir to begin his final lecture. Engineer Ahmed, the session is over to you.
Hi everyone. Today is our last session. The topic of this day is the fracturing design and the data frac analysis. Okay, so we will start with the fracturing design. First, this graph is showing the cycle for designing a frac job. First of all, we need to define the well problem, and then we can decide the treatment selection type. Then after deciding the treatment selection, we can perform the treatment design. This is including the fluid selection and proppant selection. After that, we will do the simulation to predict the treatment results. After getting the treatment results from the software of the simulation, we can identify either this design, which including the pumping schedule for frac, will justify our need of the job and the required frac geometry or not. Then we can repeat the treatment design again and reselect the fluid and the proppant to achieve our target. Then after finish the treatment prediction and we satisfied with the simulation results, we are going to do the operational stimulation program with all the small details, including the pressure tests and where we are going to set our packer, type of gun that we are going to use for perforation, everything. Okay, this program will include the operational constraints. What we are meaning by constraint, that the limitation of the equipment that we are going to use. As an example, we can say that if you are going to use a Christmas tree to do a regular frac job, so the limitation for the Christmas tree pressure rating is one of the key parameters. Also, the pressure rating for fracturing equipment that you are going to use. As example, there is 10K frac pumps and there is 15K frac pumps. According to the design or the simulation results, you can say these pumps are going to work with us or not, is suitable or not. This is what we are calling the operational constraints. Also, the packer, if you are going to use frac string with a mechanical packer, the differential pressure that the packer can hold is also a key parameter, and how you can solve this problem. As an example, if your downhole pressure, differential pressure across the packer element will exceed its limit, there's another alternative solution to reduce the differential pressure across the packer element by applying pressure in the backside, in the annulus. So all these parameters should be combined together inside the operational stimulation program to have a complete program for the frac job. Also, another one of the constraints is the limitation of the tubing itself, because you are going to use a tubing. This tubing has a limitation for the burst pressure. So the burst pressure limit of the tubing should be suitable to your maximum pressure during the operation. And according to this pressure limitation, you will set the pop-off or the vent valve setting pressure point to relieve the pressure if it exceeds any of your system maximum pressure. Then after that, after we have all the plans combined together, then we are going to schedule the job and follow the logistics to provide all the required material and equipment. Then we are going to do the site preparation to spot all the required equipment in a safe way, for sure. Then we are going to execute the job. Then the evaluation cycle will be repeated again. So the fracturing is, we can say, cumulative learning. From each job, you will learn more information about the field that you performed the job in. So from this new information and this is new experience, you will use this knowledge to design the next well. This is the critical parameters in the fracturing job. What is the most important information that we are need to design a fracturing job, and from where we can get it? As an example, as we discussed in the rock mechanical properties, Young's modulus, Poisson ratio, and formation pressure or overburden stress is important parameters. From where we can get these parameters? We can get it from logs, as we said, sonic log, or from core test and field test. We mean by field test the previously done frac job and the interpretation. The data come from the field, from the data frac, for the same field for the previous well. Okay, these parameters affecting in what? Affecting in the frac volume. Frac volume, we mean by frac volume, frac width, height, and length. These parameters which creating the fracture geometry. And with this parameter, we can calculate the frac volume itself. From the frac volume, you can design your pumping schedule, because as we said, the frac is the injected volume is divided into two main parts. First one, the frac volume itself. Then the leak-off. The leak-off, the volume of the fluid pumped during the frac job and lost inside the formation. So if we combine these two terms together, we have all injected volume during the frac job. To design any pumping schedule, we need to define these two volumes. Okay, what is affecting on the leak-off is time, height of the fracture, length. We mean by time the pumping time, fracture height, fracture length. So we can get from this data the fluid loss coefficient. Then we can calculate the leak-off. Okay, the basics of fracture modeling include of the following: prediction of the fracture geometry. We can predict the fracture geometry by using some of this one of these models. First one, the two-dimensional model, pseudo 3-dimensional model or P3D model, planar 3-dimensional model, BL 3D model, Foley 3-dimensional model. The model determine the fracture geometry by relating to the following variables: rock properties, fluid properties, and the fluid volume pumped, and the stress data. So we have all these parameters are combined together to get the fracture geometry at the end. So the fracture geometry are affected by rock properties, all the rock properties are affecting on the fracture geometry. So the soft formation or hard formation, each one have a different fracture widths, have a different fracture height according to the lithology of the barriers inside the reservoir. There is barrier above or bottom. The frac will propagate up or down according to the stress profile. The widths will be varied according to the type of the formation and the stress of the formation. Also the fluid properties itself, because the fluid properties have a very great effect on, has a great effect on the leak-off, because the leak-off is function between, relation between reservoir properties in terms of permeability and the pore spaces and everything, and the viscosity and the leak-off coefficient of the fracture fluid. So with these two terms, we can select the fracture fluid volume pumped to get the required fracture geometry. All of these are affecting by the formation stress, which affect on the terms that we said closure pressure. First of all, we will discuss the fracturing model. 2D models assume the fracture. We have three parameters of control describing the fracture geometry, which is the fracture width, this one here, fracture height, this one, and the fracture half length. What we are mean by 2D model? 2D model mean that you have only two parameters from the three parameters of the fracture geometry can be changed with the fracture half length. Okay, which means here we have this. I mean that only one parameter cannot be changed. Here, the fracture height is constant, remaining constant, but the fracture width is changing with the fracture height. Okay, so this is what we mean by the 2D models. We have in the 2D model three main types: the BKN model, KGD model, and radial model. The BKN model, we can see from this geometry that the width is changing with the fracture height. However, that the fracture height is keep constant with fracture half length. For the KGD model, the assumption is the fracture width is kept constant, while the fracture keep constant with the fracture height, but it change with the fracture half length. Here, this we can see this from this shape that the fracture width is changing with the fracture length and keep constant with the fracture height. For the radial model, we are assuming the model is like sphere. So the fracture width and the fracture height, the fracture width is changing with the fracture height and also with the fracture half length, but we assuming the fracture half length is changing according to half sphere like a radial in half sphere. So its fracture shape is kept constant according to this equation. But we are not using the radial model so much. Mainly in the 2D models, we are using PKN model or KGD. However, that the most used one is pseudo 3D model that we are using in most of our frac jobs. It is dividing the fracture into segments. Each segment has a different shape. Here we assume that the fracture is changing into dividing the fracture into different parts. Each one of the parts have a different geometry, and this give more reliability to the or the model can explain the actual shape of the fracture in the P3D model is better than the 2D models. However, that the best one for sure, the full 3D model, it is similar to the fracture simulation. We divide the fracture itself into segments, small segments. Each one of these segments, we can put all the parameters that we are using for the whole frac, which means that for each one of this cube segment of the reservoir rock, we can put the Poisson, its own Poisson ratio, its own Young's modulus, its own fluid leak of coefficient, its own in situ stress. All of these parameters can be classified into each single segment of this cube, as we can say. So at the end, you will have fracture properties for each one of these segments. So after combining the stress profile for each one of these, you will have different frac geometry inside each one of these segment or cells. So after combining the fracture resulted in each one of these cells, you will have a complete fracturing in all of them. Then you can combine these together to get the full frac geometry. So, but this needs computer processing capability is not available in our standard PC, so it is not easy to use, especially in the field. It required powerful computer, and it's not easy to be applied for the field engineers. Okay, we are now going to discuss the basic fracture calculation. How we calculate what is the term that we said, net pressure, what is the closure pressure, and what is the near wall pore friction. First of all, we have one focal point for analysis here, that we can say nodal analysis point, which is the bottom hole pressure in the front of the perforation. Here we have these two equations, the one there, this one and this one. This is bottom hole pressure in the direction of the well bore. So bottom hole pressure here equal what? Equal hydrostatic head, which is pH small, and well head pressure, and you will deduct the friction inside the frac string here. So in the other hand, this same bottom hole pressure is equal what? Equal the closure pressure plus the net pressure plus the near wear bore friction. Okay, so for this term, for this equation, it is clear that this is the easy equation. The friction and the wellhead pressure and the hydrostatic head is normal in our calculation as a petroleum engineer. However, that we are going to explain the near well pore friction is divided into two terms: the tortuosity effect and perforation friction. So we have two terms: the tortuosity friction and perforation friction. Perforation friction is calculated using this equation. We are using the Q square multiplied by specific gravity of the fluid pumped. This is including, in case that you are using proppant, the total specific gravity of the fluid and the proppant, and the dimension, the diameter of the perforation entrance in inch, and the number of perforation square. This is the shooting density of the perforation per each feet. So we can get the perforation effect from the tortuosity effect is calculated from the step rate test to calculate the total near well bore friction from the step rate test and the data frac. Then we deduct the perforation friction from the resulted near well bore friction, So we can get after that the tortuosity friction. Here is the basic graph for the fracturing job. Here we start loading the fluid. This is what was a point for question yesterday, from where I can get the fracture pressure from the frac job. Here, once we start pumping, but we should assume constant rate, as we said, the pressure will start to increase till certain point, then it start fall down. This is our breakdown point, or the fracture point. Then the pressure will start to go down until we reach the point of backing. The pressure will start to increase at the end of the job. This increase is due to the backing effect of the proppant inside the frac. Then once we stop pumping, the pressure will start to fall down to a certain point. This difference is the friction inside the tubing. This will drop very rapidly and very sharp. Then the pressure will start to stably decrease until we reach the open valve point, and the closure point will be in this part. So we explain that this difference between this point at the end of the job and the initial shut-in pressure is, all of this pressure is the friction pressure inside the frac string. So also it should be highlighted that to get the actual frac gradient, we should remove the friction effect from this point. So you should take this value of the friction here and deduct it from here, and to get actual point for the friction for the for fracture gradient without the effect of the friction during the pumping. This page is explaining what we said, what is the concept of the closure pressure and the net pressure. Here we said that we have the bottom hole pressure, and here we have the near wall bore friction. Then inside the frac we have two forces. The first one is the closing force, that is we said is in terms of closure pressure. This is the force applied across the frac itself, trying to close the frac. What is overcome this force and keep the frac open, that we call the net pressure. The net pressure is controlling the width. As much as you apply more net pressure, you will gain more width of the frac. So it is very important to design a frac job to calculate the closure pressure, to define what will be your required widths and what will be the net pressure you are going to apply inside the frac, to calculate the bottom hole pressure. From calculating the bottom hole pressure, you will calculate the expected wellhead pressure by calculating the pumping rate and calculating the friction from friction pressure equation. Then you can calculate the estimation for expected treating pressure at the wellhead. Also, to design the frac, we should define the term dimensionless fracture conductivity, or FCD. FCD is called what is calculating through what? Calculating from this term is the frac retained permeability. We said that the fracture fluid is damageable, so after also the fracture conductivity is affected by, as we said yesterday, the closure stress. So if you have certain value for the fracture conductivity, from the graphs that we said, we have graph to calculate the fracture conductivity for each proppant concentration. So you can calculate the fracture conductivity from the proppant concentration inside the frac. However, the frac returned permeability deduct from this value the effect of closure stress on the frac and the permeability that you lost due to the damage happened due to the gelling agent inside the frac. So as much as you increase the concentration of the gelling agent, you will lose more and more from the fracture permeability. Also in this term we have down there is the formation permeability itself and fracture half length. So this called FCD or dimensionless fracture conductivity. Here from this graph we can decide by this graph the optimum fracture half length according to the term of the required fracture conductivity that you want to use. So from this fracture conductivity, dimensionless fracture conductivity, you can enter here with your required value. Then you can intercept this curve and you will get a ratio between the wellbore radius and the fracture half length. By knowing your wellbore radius, you can calculate the required fracture half length to get this required dimensionless fracture conductivity. We explained this already previously. Okay, so how we are going to select the fracture geometry and the required proppant and the proppant size, concentration, and everything. First of all, we said that we define the required fracture width because the fracture width is affecting on the dimensionless fracture conductivity. From the dimensionless fracture conductivity that you are required, so you will have your own selection for the fracture width. From the fracture width, you can get the fracture half length by the curve that we show in the previous slide. So what is controlling the fracture width is the Young's modulus and the proppant concentration and design of the treatment pressure itself. As we said, the net pressure have an effect on the fracture width. The net pressure is controlled by what? Is controlled by the fluid efficiency. The fluid efficiency is affected by the pumping rate and the fluid viscosity. So all these terms are affecting on the fracture width. Also, the term remaining frac conductivity is depend on what? Depend on the closure stress, proppant type and the proppant size, proppant concentration, and the fracture fluid damage that you are using. Also, the effective frac half length is depend on what? Because there is we should differentiate between two terms, the fracture half length and the effective fracture half length. Frac half length is total frac you created and you filled with proppant. However, that if you assume assume all the fracture are conductive, or all the pore spaces inside the frac itself is conductive. However, in the true frac down there in the reservoir, the pore spaces are not only effective and can pass the flow through it. So we have a term, the effective fracture half length, which is equivalent to actual performance of the frac. So you have now in the well test, once you perform a well test for a fractured well, you will get the fracture half length. However, that from the data that you get from the well test, the fracture half length will be less than the estimated from the fracture half length estimated through the fracture program simulation. Because of what? Because of the effective of this frac half length. Because not all the probability available in the fracture between the pore spaces of the proppant is effective and can pass the flow. To design optimum frac geometry, we give an example using the nodal analysis to get to show the effect of each one of the parameters and select the optimum fracture geometry. we assume that we have a constant frac half length of 100 feet and the constant frac width, which is 0.01 inch. So we have a formation that have permeability 15 millidarcy with reservoir pressure 3000 psi and well bore radius of 6.2 inch. By using the nodal analysis, we did this sensitivity analysis assuming constant fracture half length of 150 and constant width of 0.1 inch, and did a calculation sensitivity analysis assuming different fracture conductivity to see what is the effect of the fracture conductivity and what is the optimum frac conductivity to select for design for this specific formation. So we have here, first of all, not this one. Here we have this one for 10,000 millidarcy for the frac conductivity and 100,000 millidarcy frac conductivity, 500,000, 1 million, 2 million, 5 million. Okay, from this graph we can see that as the fracture conductivity increases, the gain from this increase in the frac conductivity start to decrease. So we can select the optimum value according to the required production. Because of each one of these permeability, frac permeability will be converted into amount of money because the proppant is costing money. Also, pumping of this proppant with the required frac fluid is equal money. So the optimization here is selecting the optimum according to the production rate. From here we can see this one is the best one. After that, the production increase we can say that is negligible, and it is not matter to increase the fracture conductivity above this value. Also here to estimate the optimum fracture half length. Here we keep the frac permeability that we got from the previous one here, which is 5,000 darcy. Keep it constant with the same fracture width of 0.1, and we change the fracture half length. Fracture half length, here we start with 100 feet of the fracture half length, then 150, 200, 300, 400, 500 feet, and 600 feet, with the same concept as the fracture half length. Here it start to increase. The increase in production also start to decrease, so you can select also the optimum fracture half length in terms of production. Here we can see this one is the best one. Then after that we can neglect the small increase in the production. Then the last one, after we select the best fracture half length, we keep constant the fracture conductivity and the fracture half length to define which is the best value for the fracture width. So we are using here different value for the fracture average widths. So we can say from here this one is best one. So we can design the fracture according to this parameter. We can select the fracture permeability with 5,000 darcy and fracture half length with 600 feet or 500 feet, and the fracture width with 0.216 feet. Then we have to make the data collection. After we define the fracture, our frac geometry, we should design the pumping schedule to achieve this required fracture geometry. We have here two different parameters, we can say uncontrollable parameters and controllable parameters. Uncontrollable parameters include all the parameters related to the reservoir rock properties itself. Permeability, height, saturation, porosity, rock properties, which means Young-Poisson ratio, minimum stress, bottom hole pressure, bottom reservoir pressure, lithology and layer, type of the reservoir fluid. On the other hand, we have some parameters that is controllable, and we use actually this parameter to design the frac itself, which is the string and wellhead configuration, downhole equipment, surface equipment, completion strategy, perforation strategy, spacing, and the fracture material, including the proppant and the fluid. So we are using this to control our geometry, which means that we control the fracture that we are going to create by controlling pumping flow rate, the fluid efficiency by controlling the fluid, the frac conductivity by deselecting the proppant properties. All of this can control the frac and get the required fracture conductivity. So here, this is an example for the data that we are entering to the simulator to get the pumping schedule. This what we call static earth model. This is include all the formations that are going to be the frac are going to deal with, each sinusoidology, height, fracture gradient, Young's modulus, Poisson ratio, and its toughness. So we are putting or laminated above each other according to the lithology get from the ELAN and petrophysical parameter. Then we for the same formation here with the same organization or the distribution, we have the height. Also, we enter the porosity, reservoir pressure, specific gravity, oil saturation, and water saturation. For the tubing, we are going to use OD and weight to get the ID of the tubing and its length to calculate the friction and the rheology from the rheology parameters of the fracture fluid. Also, we are input the casing data to get the ID of the casing. Also, the perforation data is very important to calculate the perforation friction. So we add the perforation, the top and bottom in measured depths and true vertical depths and shoot density per foot. So we get the total number of shoots, then the entrance diameter for the perforation itself to calculate the perforation friction as we said. So we are using all this the data as input for software simulation to get the pumping schedule. This is an example for pumping schedule. The software is working like this. You should put a pumping schedule first, then you can calculate the results of this pumping schedule in terms of fracture geometry and frac conductivity at the end. So you should start first to put preliminary pumping schedule to estimate or predict the expected results of this pumping schedule. And if the results are not complying with our required fracture geometry, we can modify this pumping schedule to get the required fracture geometry. So first of all, the first pump bed in the Mainfrac is the bed. Bed is linear cross-linked gel without proppant to create or initiate the first fracturing, and then we start pumping the fluid with the same fluid type with proppant concentration. Here we're starting with pumping proppant inside the newly created frac gradually. So we start with 1 ppA, 2 ppA, 3 ppA, 5 ppA, 6 ppA till the flushing. What we are meaning with ppA, 1 ppA means that 1 pound of proppant per each gallon of the frac fluid. 2 ppA means the proppant concentration inside the frac fluid is 2 pounds per each gallon. So normally the bad percentage is varied between 30 to 40% of the dirty volume. With what is meaning of dirty volume and clean volume? Clean volume is the fluid, frac fluid pumped without estimation of proppant volume. Dirty volume consider estimation of the proppant volume within the volume of the fluid pumped. So we have here the percentage of the bad is 41 per clean volume and 37.7 for the dirty volume. Okay. So we are controlling the fracture conductivity by changing the proppant concentration and the volume of stages of high proppant concentration. So as you increase the concentration, the volume of high proppant concentration, you will increase at the end the fracture conductivity itself. But the risk here, as you increase the proppant concentration, you will increase the tendency of the screen out by early bridging of the proppant. So here the most important point is what is to select the maximum concentration and the maximum volume of the proppant that will not result in early bridging and screen out for the fracture. So we are keep trying to change the proppant percentage and the proppant concentration and the volume of each one of the high concentration proppant stages to get the maximum conductivity or the required conductivity, while keep the proppant pumped safely without any early bridging of the proppant drains. So we are keep trying of this pumping schedule until we get the required and the optimum fracture geometry. Some consideration should be taken here from the perforation side, because in some cases, some of the companies are using 180 phasing perforation guns. Here what we are calling by phasing, we have the phasing is the angle between any two shots of the perforation, between the angle between two shots, phasing of the two shots of perforation with each other. So in sometimes the perforation are what we call is 180 phasing, which means that one shot in one direction and the second shot in the opposite direction. The 360 phasing, it means what? It means that all the shots are in the same direction. So as the phasing angle decreases, the possibility or the tortuosity effect friction is decreasing. Because of what? The tortuosity effect is if we have the fracture, our fracture in this, the minimum stress, the fracture will propagate in this direction, as an example, here and here. This is according to what? According to direction of minimum stress of the reservoir rock. And in case our perforation phasing is here and here and here, this means what? The fluid that we are going to come out of this tunnel of the perforation need to turn over around the wellbore till it reach the point here to propagate in the direction of the minimum stress. So this means what? This means that in this area around the wellbore, we will have high friction due to this turning over of the fluid inside the reservoir rock. This area that is called the tortuosity effect, or this friction happened here is tortuosity friction. So in order to reduce the tortuosity friction, we need to reduce the phasing between the shots during the perforation. Also to reduce perforation friction, we need to use big entrance holes or big hole perforation guns. This will increase the entrance hole diameter and it will decrease the perforation friction. Also, for horizontal wells, we should select or design the orientation of the horizontal directional that we are going to drill according to the frac required interception with the well bore. Which means, if we see here, this is one multilateral well, the angle between this one and this one is 90 degrees. This frac, this 1, 2, 3, 4, 5, 6, 7, 8, 9, all of them have the same direction. This direction is depend on the minimum stress direction, as we all agreed. So the interception between this hole and the frac will depend on your direction of drilling, not you cannot control where the frac is going to propagate. It will propagate according to minimum stress direction. So if you need to increase the contact area between the well bore and the frac itself, you need to select this direction to have the well bore design to be perpendicular to the minimum stress. Here the well is drilled in the same direction of the minimum stress. So to select which kind of directional well that you are going to drill, we should know where is the minimum direction is to select the best direction to drill the well. Okay, the last topic in our session today is the data frac analysis. In data frac analysis, actually we do two tests, the main two tests: closure test and calibration test. Closure test, we make a step rate test and then stop at constant rate, increasing rate, then constant rate, then we stop to get the closure pressure. For calibration test, we are pumping fluid with constant rate with the same fluid type that we are going to use during the frac job. This is because of what? To get the fluid efficiency. So because of this, we call it calibration test. But at any case, it is better to do the closure test and the calibration test, both of them with the same fracture fluid that you are going to use, which means some companies are using linear gel to do the data frac, and some other company are using cross-linked gel to perform the data frac. The companies that are using the cross-linked gel get better results from the data frac than the companies using linear gel. Because of what? The leak-off for the linear gel is totally different than the leak-off of the cross-linked gel due to difference in viscosity between these two types of fluid. So when you get the closure pressure, you will get closure pressure and you will get a value, correct value for closure pressure, because it is related to the rock, not to the fluid. But the fluid efficiency and the calculation for the required volume during the frac job will be totally different between these two companies. And if you're comparing between data frac job from Halliburton and another one from Schlumberger, you will discover this truth, because the fluid efficiency will be totally different. However, we have two neighbor wells, and you will have totally different value for the fluid efficiency, because this company is doing the frac job, the data frac job with linear gel, and the other one is doing with cross-linked gel. So it is better to use it with cross-linked gel to get a value for the fluid efficiency equal to what you are going to face during the Mainfrac job. Here we are doing the step rate test and the calibration test. Here they mention we are doing with linear gel, this step rate test, and the calibration test we do it with cross-linked gel, because we said from the calibration test we are going to get value for the efficiency. So it is required to get this efficiency value using the same fluid that you are going to using the Mainfrac. However, that for linear gel we will get new pore friction value and closure pressure, and both of them are not related that much to the type of fluid. Okay. Can pass this. This is a typical shape for the data frag job. We can go for the calibration injection test directly to get how we are going to calculate. This is the shape of the data frag interpretation using the G function plot. This is the most famous way to make the interpretation for the data frag. We have the term the G function, and we have bottom hole pressure. This is the raw data without any analysis. We have derivative and superposition derivative. Here, how we calculate the G function. The G function is calculated from what we call dimensionless time. Dimensionless time is T. This T is what is time in seconds from the initial shut-in pressure till the point that of recording pressure, the time of recording pressure. So you have here pressure value here recorded at each one of these points. Okay, here first one here is recorded at the initial shut-in pressure, which is our 0 time. This one is recorded after 1 second, 2 seconds, 3 seconds, 5 seconds. So if we are going to calculate the dimensionless time at this for this pressure value, so this means that this 2 seconds, this 1 second, 2 seconds, so the time T is 3. T bumping is the time of bumping during the data frag job. Total bumping time since start the bumping till the initial shut-in pressure point. Okay, so by this equation we calculate the dimensionless time. Then we calculate the G function by this equation by knowing the dimensionless time. Then we can calculate the efficiency by this equation by knowing the G function at the closure point. So this is the G function at the closure point. So from this value we can calculate the fluid efficiency. So how we are going, so we know that now that how we calculate the G function. Then we draw the bottom hole pressure against the G function. This is the red line. Then we make the derivative of the pressure against the G function. This is the purple line. And the blue line is the superposition derivative by get the derivative and multiply it by the G function itself. Then we can get the value for what we call the superposition derivative. So we draw all these three values for the pressure and its derivative against the G function. How we can calculate or identify the closure pressure point. Here, this is a typical G function analysis for a data frag job. Here, from we are depend on the superposition derivative to define the closure point. So the closure point is started, the superposition derivative start almost linear till we get the value. Then the slope of the superposition derivative curve start to increase dramatically. This point that we select as a closure point, then we can intercept the closure axis to get the closure value of the G function at the closure value at this point, as we decided as a closure point, then we can intercept the pressure axis to get the closure pressure. We have here different typical graph for the shape of the derivative and superposition derivative for different cases. The normal cases or standard cases, the line is the slope is kept constant till the point where slope is changed. So we have this straight line. Once the slope is of the superposition derivative start to change, we select directly this point as the closure point. In some other cases, we have hump here for the superposition derivative before it is become again straight. Then at this point, the superposition derivative slope started to change. So we select this point as the closure point, not this one, because of what? This is what we call a small fissures opening leak-off. We have a small fissures inside the reservoir that is open after applying the pressure inside the frac. Then it is closed first. Then our main frac is closed after. Okay, so if we see this hub, because somebody in some cases maybe select this point as a closure. No, it is not correct. You should wait till you see the true closure here. Then this graph is showing that we call height recession during the data frac. What is the meaning with height recession? If we see the hump is going down like this, then it is start to become straight, then this point is our closure. This means what? This means after bumping, the height of the fracture start is still growing even after stop bumping. This means what? This means that have a low stress formation that cannot keep the fracture out of growing after stop bumping, so the fracture even keep growing in height after stop the fracture. In this case, this graph, we didn't see any closure point. This means what? This means that the fracture is keep growing in direction of half length, even after stop bumping, and we didn't reach the closure point. This curve is appear in very, very tight formation, and we didn't see here any closure formation because of there is almost no leak off from the frac fluid bumping. Okay, there is another equation that we can calculate the fluid efficiency from it. We can calculate the fluid efficiency from the closure time, because after you get the closure time or the G function for the closure point, we can calculate the time of closure. Then we have the injection time, this all in minutes. So we can apply this equation to get the fluid efficiency. This is called Noether equation to calculate the fluid efficiency. Okay, I'm finished. Any questions?
Okay, thank you so much, Engineer Ahmed, for this informative lecture. In the meantime, we have a lot of questions. So the first one is asking, what are the additional factors to take into account for the fracturing design in case of horizontal wells?
As we said, the fracturing of horizontal wells, you should take in consideration the direction of the minimum stress and the orientation between the frac and the well bore itself to design the well direction before starting the drilling process itself. So you should orient it where you are going to drill to have the point of interception between the. I'm trying to get the slide. Here. as we said, that this design is better than this one, because this, you have a contact area between the wheel bore and the frac itself bigger than this, because the contact area between the frac and wheel bore here is very small, very narrow. This will affect on the conductivity of the frac itself and the deliverability of the frac to the wheel bore. However, so it is generally it is better to select this direction of the horizontal well. However, this problem is limited the number of the frac that you can make from one hole. So if you see here that the fracture height here, is in the same direction of the wheel bore, so you are not able to do many fracs from the same wheel bore, because it is limited the number of the fracs that you can gain. However, that in this design, if you want to cover the reservoir with more number of the fracturing job, or number of stages of frac, you need to design the wheel bore in this direction, because this will allow you to do bigger number of the frac stages. So in the very tight reservoir, especially in the shale gas, they are selecting this design to let them make a lot of fracs to cover bigger area with the reservoir with fracturing, because any part of the reservoir rock will not reach by frac, it will not be shared to production. So they need to do a lot of frac to cover all the reservoir rock. So they select this design. If you have a normal permeable rock, it is better to design the well like this. This one. Okay.
Okay, thank you so much. Regarding the horizontal drilling, someone is asking, the horizontal drilling and the fracking. Someone is asking, how can we solve the conflict between horizontal drilling and fracturing, since each one of them prefers to perpendicular to the minimum stress?
This at the end should be solved according to discussion between the two teams, the stimulation team and the drilling team. For sure, the drilling will select to drill in the perpendicular to the minimum stress because it's faster and easier. However, if it is not benefitable to the fracture design, because our control parameter at the end is the production rate. So we will select the best for production regarding the situation, what is the easier for drilling. So, and at the end, money talks. So what we will control in this, you will do the both cases design. You will do a complete design for drill the well in the direction of minimum stress, and another design for well perpendicular to minimum stress. And at the end, you will compare the production and the gain in production, if it is justify increasing cost in one of option to other, will justify the reason why you are selecting this design or this one. So the cost estimation and the production gain will control you at the end.
Okay, thank you. Another question, is the optimum and the effective frac length are the same?
No, they are not the same. Optimum frac length, we calculated the optimum frac length in terms of production. The optimum frac length is the length of, if we increase the fracture length after this fracture length, if we increase the fracture half length more than this value, we will not gain production more than this. This is the optimum. Okay, so we define the optimum. The effective is totally different. Effective is calculated after you perform the frac and you have actually fracture half lengths that you created, but in terms of production sharing, you are not seeing this all lengths that you create. This is due to what? This is due to the damage of fracture fluid not allowing the fluid to pass across all the created fracture half lengths. So you have the effective half length, which is equal to the volume of the fracture that you are using actually to pass the hydrocarbon through it.
Okay, thank you. Another question, how do we determine the ratio between the clean and the dirty fluid?
As I explained this point, that the clean fluid is total volume of the, you mean that this percentage, yes, here, this percentage of the bed. So we have here total stage volume, clean volume, and we have total stages volume, dirty volume. So, okay, the difference between dirty and clean, the clean is total liquid pumped without proppant, and the dirty volume is total fluid pumped in addition to the proppant volume. So usually we'll have the dirty volume is bigger than the clean volume. So we get the bed volume and divide same by the total job volume. One time by the total job volume in clean and one time by total job volume by dirty volume. So we will have two different percentages. However, that the bed volume is constant in the term of dirty and clean because there is no proppant at the bed. So the bed volume is constant. However, that the clean volume is smaller than the dirty volume. So the percentage of the bed from the clean volume will be higher than the value with dirty volume because the dirty volume is bigger. Easy.
Okay. Another question, can we frac in reverse regime?
What you mean by reverse regime?
I think he can elaborate for the one who was asking this question. And then we will go to another one. Okay, so another one is asking, is the bottom hole pressure during stimulation is locked by a downhole equipment or is calculated from surface data?
Again, can you repeat this one again?
Okay, is the bottom hole pressure during stimulation locked by a downhole equipment or calculated from surface data?
Logged, what does it mean?
Logging.
Logged, recorded, yeah. You mean?
Yeah.
Actually, so, we have both options. In some cases that in normal cases we calculate the bottom hole pressure from the surface data. So we calculate the friction, we calculate the hydrostatic pressure, and we are measuring the wellhead pressure. So by combining the three terms together, we can calculate the bottom hole pressure. In some rare cases, we are using surface leak readout pressure gauges, so we can get live reading for the bottom hole pressure. This can be applied in the critical wells that we need to see actual bottom hole pressure during the job. So you can have both, either to measure it during the job or to have it calculated. Okay.
Okay. Okay, another question. What workflow to take to get the stress profile from logs?
Again?
What is the workflow to get stress profile from the logs?
The workflow to get the stress profile. Okay. Yeah. From the logs, you need, as we said, the gamma ray, and you need sonic dipole log. Sonic dipole log, we said to have the compression, shear and compressional wave. Then you have equations to apply to get the value for each one of the rock mechanic properties. Okay, so you can do this from the logs, and you can compare it from actual data that you get from the core analysis to check your calculation. But however, that we should differentiate between two type of the reservoir rock properties. We have what we call static reservoir rock properties and dynamic reservoir rock properties. The data recorded from the log, we call it dynamic reservoir properties because of it measured using the sonic wave, and sonic wave is dynamic. However, that the data is coming from the core is called static because we measure this data in a static condition, and the most accurate is the static condition. So if we wanted to compare between the data is coming from the core and the log, it will be different a little bit. But we can in most cases we are depend on the data come from the sonic log. But there is no actual cycle. It is one step of the fracture design cycle. So we cannot say that it is one cycle by itself. It is part of the fracturing job design cycle.
Okay. What are the recommendations for the final design in the case of height precision?
This is according to the well situation itself. So if we have height recession and we are fracturing in reservoirs that there is no clear contact, water contact in this well, so the height recession will not just will affect on the fracture geometry that is going to achieve with this frac. So height recession means what? Means the frac is gain more height than your estimation. So you should increase the fracture volume a little bit to overcome this height recession to achieve your required fracture half length, because the fluid will create more height than your estimation, and this will affect on the fracture half length. So the idea is to increase the total volume to overcome this and achieve your fracture half length. In other hand, if you are fracking in zone that have a near will poor contact, this means that there is great possibility to the frac to reach this contact. This means what? This means that the frac, the mobility of water is higher than the mobility for hydrocarbon. So this means that once you hit the water zone, the frac will produce more water than oil. So this situation is not preferable. So it should be, this decision should be taken according to the working between stimulation team and the frac team, either to cancel the job in this case if it is risky to hit the water zone and to produce water, or if the risk is acceptable and water production will not be that much. So this decision should be in combined between these two teams.
Okay, we have like final questions. So is it better to reduce net pressure in the main job if we have height precision during the Minifrac? And if we have no stress barrier, is better to have to reduce the net pressure to make longer frac?
For the first part, if we have height recession, it is better to reduce the net pressure. For sure, you will reduce the net pressure by reducing the pumping rate. reduction of the pumping rate will reduce the height and will reduce the net pressure. However, this is decision according to the estimated fracture widths, because if you reduce the net pressure, you will reduce the fracture widths, by the way. At the same time, so you need to decide either to change the proppant size, to reduce the proppant size you are going to use, and at the same time you will use a fracture conductivity. So you should decide what will be the fracture widths after reducing the net pressure, and at any case it should be equal 3 times bigger than the maximum diameter size of the proppant used. So if it is fit this condition, so you can do it, no problem. If it is not, it will be very risky to reduce the net pressure, so you will have the high risk for the early screen out due to proppant bridging. What is the other part of the question? If we reduce the net pressure, in what case?
If we have no stress barrier, is it better to reduce the net pressure to make longer frac?
If we have no stress barrier, so this means the fracture will keep high, will keep growing. So if you will reduce the net pressure, yes, you will gain more fracture half lengths for sure, because your reduction in the net pressure will reduce. You will also reduce the net pressure by reducing the fracture height, by reducing the flow rate, pumping flow rate during the frac job. This will control the height a little bit, but this will also reduce the net pressure as he asking. So for sure you will get more fracture half lengths, but you should calculate the widths very carefully, and to be sure the proppant size that you are using is suitable for this condition.
Okay.
Because you will not gain anything if you get early screen out, and you will not gain the required height because the proppant will bridge early inside the frac, and all the frac you created during the bed stage, it will not be propped, so it does not exist.
Okay. So in case of naturally fractured reservoirs, what are the critical parameters when designing hydraulic fracturing?
In naturally fractured reservoirs, the most critical parameters is the fluid efficiency, because the naturally fractured are opening during the fracture job, so it is increase the leak off. So we should calculate the net pressure very well to guarantee that the fluid efficiency and the pumping schedule will achieve the required frac geometry.
Okay, so regarding the first question that we missed, can we frac in a reverse regime? He meant by a reverse regime when overburden is the lowest stress.
Yes, we can for sure. But in this case, the frac direction will be horizontal, because the frac is perpendicular to the minimum stress. So if the overburden stress is less than the formation stress, the frac will be horizontal. If it is suitable for him like this, okay, we can proceed. Yeah. But there is a lot of situation that the frac is doing like this.
Okay. Okay, regarding our time limits, we will not be able to take the rest of the questions, but there's a question from yesterday's session for recommendations for some books or materials to take into consideration regarding hydraulic fracturing.
Okay, I prepare some of PDF files that I can send it to you to share for the group.
Perfect. Okay, thank you so much, Engineer Ahmed, for answering all these questions. This concludes our quick Q&A session and our last session. Thank you so much, Engineer Ahmed, for the great lecture and for this valuable course. I believe the participants also have learned everything very well. At the end, Engineer Ahmed, we highly appreciate your time and efforts that you have given us for educating us about hydraulic fracturing in the oil and gas industry. And we expect to have some more from you in the future, inshallah. Dear attendees, thank you so much for joining us from all over the world. I hope you enjoyed our course. Until then, please take care, stay safe, and have a good evening.